Okay, this is a basic session, so I will go back to basic and I will basically describe the three main mechanisms, which are diffusion, convection, and adsorption. Diffusion is a movement of molecules across a semi-permeable membrane in response to a concentration gradient. The driving force is the concentration gradient. The driving force of convection is the transmembrane pressure that makes actually possible to transport some solvent across the membrane and then bring solutes with it. The main mechanism of diffusion is used in hemodialysis, where basically you have dialysate and you don't need any replacement solution. The convection mechanism is mostly used in hemofiltration when you need a replacement solution because of the excess of ultrafiltration produced. Diffusion depends on several variables, including the diffusion coefficient of the solute, the temperature, the surface area, concentration gradient, and the distance for diffusion, that in most cases is identified by the thickness of the membrane. Free diffusion coefficient of molecules depend on their size, molecular weight or molecular size in terms of radius. And as you can see here, as you move towards larger solutes, the diffusion coefficient tend to decrease significantly. But in some cases, thickness of the membranes is not the main resistance because, in fact, sometimes you have stagnation layers at the blood membrane interface or at the dialysate interface, and therefore the distance for diffusion may actually be wider than one can expect. More, there is interference of proteins that may create a pseudomembrane at the blood membrane interface. So we have different filters with different characteristics, and we use different filters depending on what kind of blood flow we expect to have. There's no point to use a very large surface area filter if your blood flow does not exceed 200 mL per minute. You can only exploit the capacity of a large filter if you go up with blood flow higher than 300 or 400. Also, diffusion coefficient and clearance, therefore, are expected to respond to a specific molecular weight criteria. However, there might be factors that interfere with the ideal line, and these are presence of electrical charges, lipophilic structure, protein binding that reduce the expected clearance. Other question like spherical configuration, if you have a very rounded molecule or high filtration rates, actually diffusion tend to be better. Everything is somehow depending on the polarity of water that has electronegative and positive regions and tend to actually link molecules through hydrogen bonds. Now, if you take, for example, a molecule like phosphate, that can be phosphate acid or can be monobasic, bibasic, or tribasic ionized, you may have a different interference of water. For example, this is bibasic ionated phosphate with two molecules of water surrounding the molecule of phosphate. But if you have a tribasic phosphate, you have actually a dodecahydrated shell around the phosphate. Also, the interaction of membrane with water, the possibility to have hydrophilic or hydrophobic surface can make a very different behavior. If you have a hydrophilic surface, you have a continuous fluid phase because the solvent tends to wet the membrane, and therefore this can be very good for diffusion. But if you have an hydrophobic surface, then you have discontinuous fluid phase in pores, and this can only be overcome by convection. Convection that depends on the ultrafiltration rate, so the amount of fluid that you transfer across the membrane, and a value that we call sieving coefficient, which is the relationship between concentration of the solutes in the ultrafiltrate and in plasma water in the absence of gradient for diffusion. So the ultrafiltration depends on the ultrafiltration coefficient of the membrane. At the given transmembrane pressure gradient, you got a certain amount of ultrafiltration. And this line described the KF, the permeability coefficient, which is basically depending on this transmembrane pressure based on hydraulic pressure and oncotic pressure, the typical Starling forces. The sieving coefficient is described by a curve, and we have the final value of sieving close to 0.1 that we define cutoff, or the initial decrease of the curve when the value of sieving is 0.9 that we call retention onset. Ultrafiltration is a process of production of plasma water solvent from whole blood in response to a transmembrane pressure. It contains crystalloids, but not cells nor colloids. And this is a typical condition of a low flux membrane or high flux membrane. You see at the given transmembrane pressure, you have a very different amount of ultrafiltration produced. However, the behavior of the membrane is not ideal. And if you increase your transmembrane pressure, your filtration fraction increase, and you get a series of molecular protein that somehow form a layer at the blood membrane interface, and the permeability of the membrane starts a decay and the function is not linear anymore. This phenomenon is called concentration polarization. This is also the reason why ultrafiltration rates tend to decrease over time for a given transmembrane pressure, showing that the permeability of the membrane over time changes significantly. And also the sieving coefficient curve tend to decrease significantly over time. So there are membranes and filter-related problems that may actually decrease the efficiency of the system. Sieving coefficient can be close to 1 for some molecules at the beginning, but it may be very different from 1 if you, for example, use pre-dilution. In the filter, the sieving is still 1, but if you calculate the true relationship between the effluent and the plasma water entering the filter, you see that pre-dilution may affect differently the performance of the membrane. At the same time, if the membrane gets somehow clogged, at that point, your sieving coefficient may be very different over time. If you measure, for example, the sieving for different solutes, including creatinine, which has normally a sieving coefficient close to 1, you see that over 24 hours, and when you start using the filter for longer time, the curve of sieving may be significantly reduced, especially if the anticoagulation approach is not appropriate or optimized. The membrane can actually be clogged and display some different behavior compared to what you expect. Filtration fraction is one of the major determinants, because if you have high ultrafiltration rates in presence of low blood flow, your filtration fraction goes much higher than the optimized 15 to 20%. And at that point, as you can see here, when you increase filtration fraction, your sieving coefficient can be strongly affected, because the membrane is not just the membrane itself, but the membrane starts to be a membrane plus a kind of a cake of proteins at the blood membrane interface. And it is, of course, a dynamic equilibrium that you can achieve, but this is the level of protein deposition that you can get when you have high filtration fraction. Membrane sieving coefficient may differ significantly depending on the type of membrane you are using: low flux, high cutoff. This is the most recent medium cutoff membrane. And as I mentioned to you, it is not enough to measure just the cutoff value. You need to measure the retention onset. That can be very different depending on the membrane type of pore distribution. Also, we know that solutes may not have a rounded configuration, and what you may be interested on rather than molecular weight is the molecular radius of this surrounding area, because the chance to remove this solute is comparable to a molecular weight which is much higher than what you would expect. In general, we know that small solutes can be removed by diffusion, and that's why their clearance increase with blood flow, while large solutes tend not to increase with blood flow, and if you want to remove more of them, you need to increase convection. Surface area is important only when you exploit higher blood flow and only for small clearance, while dialysate flow rates depend very much whether or not you work at the saturation level. In CVVHD, for example, you almost have completely saturated the dialysate, but in standard intermittent hemodialysis, you are actually working much below the level of saturation. Hemodiafiltration is a combination of hemodialysis and hemofiltration, combining well diffusion and convection. And in the past, we used to have low flux membranes that were characterized by a very thin membrane optimized for diffusion. We had thick membranes, hydrophobic, optimized for convection. And recently, we have membranes that are optimized for hydrophobic, hydrophilic configuration with reduced wall thickness, and finally, they can be combined in diffusion and convection. If you use a thin, low-flux membrane, it can be good for diffusion with small molecules, certainly not for larger molecules. If you use a thick, high-flux membrane, it can be good for convection, but certainly not for diffusion because of the distance. And if you use thin, high-flux membrane, you can remove solutes both in diffusion and convection. The three mechanisms operate in different ways depending on the transmembrane pressure. Just to remind you that in hemofiltration and hemodiafiltration, because the ultrafiltration exceeds the amount of fluid you need to remove in the patient, you need to apply some kind of replacement solution. How does convection help diffusion? Well, it is clear in this slide that it doesn't help too much for small molecules, but actually you can have a dramatic increase in removal of large molecules when you apply high level of convection. We have described the importance of membranes and holofibers as structures that avoid maximum resistance for transport. And in fact, in some cases, we have seen that the resistance to transport can be higher in the blood compartment rather than in the membrane itself. That's why we need to have a very nicely distributed flow in dialyzer, and blood ports are trying to ensure the fact that we do not have a privileged flow in the center of the filter as it was in the past. In the past, we had blood flow entering the filter. At that point, there was a kind of increase in the velocity in the central part of the bundle of the fibers, while in the peripheral part was very, very slow flow. In the most recent dialyzer, this has been overcome, especially studying the fact that when you study blood is a non-Newtonian fluid, and if you treat the blood at high velocity, viscosity decrease, while if the velocity of blood goes very slow, you have the formation of a red cell aggregation and the viscosity tend to increase, and then clotting is becoming easier. Also, inside the filter, you have an area of maximum filtration rate at the proximal level, minimal filtration and back filtration in the distal part, and we have studied this with sophisticated methods. For example, if you reduce the inner diameter of the fiber, the pressure drop increase and back filtration tend to increase, but also tend to have a much better flow velocity inside. And this parameter that we call wall shear rate, which is a gradient of velocity between blood and the wall of the fiber. If it is very high, this generates an effect of shear, an effect of cleaning on the on the surface at the blood membrane interface, while at low shear rate, you tend to have accumulation of proteins. And that explains why, for example, if you have a much higher flow or reduced inner diameter at the given blood flow, you tend to have higher ultrafiltration rates in this type of fibers. The design of the dialyzer is important, although we find ready-to-use dialyzers, but we come from a history where we suggested how to design dialyzer. And in a large fat dialyzer, the pressure drop is minimum and you dissociate blood flow from obligatory filtration. While, I'm sorry, I forgot to close the phone. And if you have a thin, long dialyzer, actually, the pressure drop is very high and the obligatory filtration will be much higher. At this point, we know that when you have, for example, a reduced inner diameter, your wall shear rate will be higher and the effect will be much higher clearance of large molecules because of higher internal filtration. One last thing, when you have a dialysate flow rate, the velocity and the distribution of dialysate is important, because if you have a kind of a high filtration rate, you bring plasma water at the same concentration on the other side of the membrane, and the gradient for diffusion is lost unless you have a nice cleaning effect from the dialysate effect. So you may have stagnation layer outside the fiber, and the distance for diffusion may actually increase. For this reason, you have to study the distribution flow in the dialysate compartment. And what we did, actually, we analyzed with the same CT scan technique the distribution of dialysate flow rate in original dialyzer. Again, there was a maximal flow velocity at the periphery and minimal at the center, exactly the opposite of what we saw with the blood. And so there was a kind of blood to dialysate mismatch. Now, the change came when we started to use fibers that were ondulated and allowed for a nice distribution of dialysate flow rate. And here you can see how much the dialysate flow rate is more homogeneous compared to other configurations seen in the past. We have already discussed about membranes. The only thing I want to mention is that if you want to remove molecules that are beyond the capacity of the porosity of the membrane, which is basically located at the blood membrane interface, and it is beyond the value of cutoff of the membrane, you have to design a different series of pores. And this is what has been actually generated in case of high cutoff membrane. Or you might need to have membranes that absorb on the surface. And this was the first test we did years ago with immunohistochemistry, where we analyzed the capacity of absorption. Absorption may occur for different forces, van der Waals, ionic bonds, hydrophobic bonds, and this is what sorbents actually utilize. They can be natural or synthetic, and if they are synthetic, they are often functionalized monomer or, I'm sorry, the slide went a little bit nuts. To get an effective sorbent therapy, you need an effective and safe sorbent material, an adequately designed sorbent cartridge, and an optimal utilization of the available surface. In fact, when you adsorb, you have an external phase to the sorbent, you have an internal phase, and then you have a surface diffusion and absorption on the pores. And also we studied the distribution with the most recent cartridges by dye injection, and the homogeneous distribution is also seen technically from outside. One of the problems is that the sorbent very often have only utilization in the external part, as you can see here with the colored cytochrome C. So the problem is to try to get enough porosity to get through the sorbent and expand the surface area. In case, for example, of uncoated charcoal, we have a large surface area. In case of hydrophobic resins, we have less surface area because we need to coat the surface, and this may limit the transport of solutes inside. So just to summarize what I just told you, we have diffusion, and we mostly use this in hemodialysis. We have hemofiltration, and we use this with convection. We have hemodiafiltration that combines the two. And finally, hemoperfusion, which is a direct adsorption provided by a sorbent material. We can use these different mechanisms, and different techniques actually combine these different techniques and mechanisms of solute removal. Thank you very much.